check if the Yuan Jia here. Wang Lingjing, Wu Dongjie, Xiu, Li Mingxiu, you. Oh, then Gong Siyu. Who is Gong Siyu? Siyu. Gong Siyu not yet. Okay. Gong Jingbo, I know. So you guys are my advice. Okay. So you can meet me during my office hour, or if you want, you can make another appointment. Slowly, I will learn all your names, hopefully. I think I saw Gong Siyu name last semester as well. He or she? He. All right. Let's have a warm-up question or any question from last week before we start. No. Also, I posted up assignment 1. Hopefully, you already start doing it. Okay. You have 2 weeks. You can collaborate with your friends. Okay, but you cannot copy from each other. So whatever you write that you submitted must be written on your own. Okay. You can discuss idea, but you have to write on your own. Okay. Plagiarism will have a serious punishment. Okay. What else? As I think I stated in the Moodle, we will submit through another platform called CrowdMark. Okay. After I receive the details, I'll let you know. Okay. What else? I also posted out the guideline for project 1 already. Hopefully you see it. It's in the course information. I can't show it now because I'm not sure why I can't log into the Moodle. So what I said last time already written black and white in course information. Hopefully you start thinking about it. If you have any problem on projects or assignments, you can come and see me during my office hour. Okay. And also tutorial question, make sure you do on your own. Okay. If you have meet any problem that you don't understand, you cannot solve, you can bring it to me as well. Okay. So far, that's all for admin stuff. Okay, let's do one exercise. Let's compute this infinite sum. Everyone see it? What's the sum of this series? Does it converge? Yeah. Converge to what? 103? How do you do that? Huh? How do you do that? Geometry series. Okay, so what's the formula you use? What's the A? Okay, what's your R? 144 as well. Okay. Yeah. And since this is geometry series, right? Another way to see it is you look from a square with length 1. Square with length 1. Okay. So you can cut your square into 4 parts, half on the horizontal, half on the vertical. Okay, so the first term is the one of the area of the square. Okay, and then you can continue cutting one of the square into half again. Okay, 1/16 is the square of the subsequent one of the square in the subsequent square. Okay, and then you can repeat this procedure. Cut the square into half again, so you get 1/16, and so on. So that you can so what you get is 1/3 of the square. Okay, so you will like forever. You can imagine you can forever filling this part, and you break the square into three parts. So this is a method known to Greek or Babylonian 4 times. That's why these are called geometric series. Right? Okay. Okay, another thing, another one. Let's try another one. What is the infinite series of this guy? Does this converge? Huh? Divergent? This is a divergent series. Anyone have any objection? This diverge? Any objection? I think using the last theorem we show, right? If the sum, the infinite series converges, then each term in the series will converge to 0. Okay, but since this limit to every term, you look at the sequence of every term appearing, you take the limit and then you go to infinity, then that's mean the series doesn't converge. Okay, but this series has an analytic continuation. Okay, which means if you look like it at the complex plane, this sequence actually converge to negative half. Sorry, negative 1/12, if I'm not wrong. Something negative, not wrong, right? Okay. So negative 1/12. If you look at the Riemann zeta function and then look at the analytic configuration, you can see this. Another way to see it is from a Ramanujan point of view. Okay, so what Ramanujan did is, I don't know it converged or not. I let the infinite series equal to some variable, some number, and then see if I can hook up that number. For example, 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1. Okay. Last time we also see that this limit of this sequence of term is alternating, right? So it doesn't converge. Okay. Also, that means the infinite series also don't converge. But let's say we let it be 8. Okay. Let's say equals to some number. Can we do some trick to find this number or not? So what we can do is we add two such series together. Okay. So what you can see is you can make the term at the back disappear by cancelling out with another infinite series, infinite terms, infinite sequence. I mean. Yeah, another sequence. Okay, right. Then what we get is 1 equals to 2a, which implies a equals to half. So this thing is equal. Okay, although this is a bit heuristic, so this is actually called the Ramanujan summation. This is not in this syllabus. We are not doing this, but you could do it as your project. Yeah, you can write about something on this Ramanujan summation. Okay, and then using a few more series, you can show that. Okay, actually, I just tell you the series. Actually, if you can find out what is 1 minus 2 plus 3 minus 4 plus 5 minus 6, make it equal to b, then you will manage to find 1 plus 2 plus 3 plus 4 plus 5. Adding up all the natural number, you get minus 1 over 12. Okay? Yeah. So this one has something to do with complex analysis, I guess. So you could use this as your project if you like. Okay? So infinite series equal to some weird number. And these have an impact on quantum physics. Okay? All right. I give you another potential topic to do. Please talk to me about your project, definitely. Otherwise, project is quite subjective. So, yeah, quite subjective. So we have to discuss well. Otherwise, you won't get most of the mark. Okay. Anything want to say about? Okay, so telescoping. Okay, skip that first. Okay, so let's pick up from where we stopped last time. We stopped at exactly this theorem here. Test for convergent, divergent. Okay, so the test is by considering the contrapositive of this statement here. So how you gonna prove this statement? Okay, so we want to prove that the limit of an is equal to 0. Right? So suppose Sn is the n partial sum of the infinite series. Okay, since the infinite series converges, the infinite series equal to some x for some finite x in R. Okay, so far so good. So far so good. Okay. Okay. In this case, what is an? How can you obtain an from Sn? Huh? Okay, so an is equal to Sn minus 1. Does everyone see this? Okay, so Sn is summing 1 to n, and then Sn minus 1 summing 1 to a1 to an minus 1. So you take away 1 to n minus 1, so you get left with an. Then you can apply limit on both sides and see what's going on. Okay. So what happened to right hand side? There are two sequence of which are converging. Yeah. So they are converging, then we can bring the limit into the to the expression, right? By the property of the limit of convergent sequence. Okay. So what do you get for these two limits? S and okay, S. So n-1 is just shifted as n, so it still converge to the same n because the limit we only care about large n. Okay, so you get 0. Okay, so let's try and use this theorem. Okay, so let's use this theorem. So determine whether this infinite series converge. Okay, so we want to determine whether these diverge or converge. So what can we do? So let's look at the behavior of the term in the series. Okay, so what should we do? Maybe we get rid the highest power of n first, meaning divide by n cubed on both sides, where we get 1 over 3 plus 2 over n. Okay, so the limit of this is 1 over 3, which is not 0. Then you can apply the contrapositive of the test, which means the series diverges. Okay. Can you say anything if this sequence actually equal to 0? Yes or no? Let's say you have a limit of your sequence equal to 0. Can you say anything about the infinite series? No. Okay. Because this proposition only go one way. If the infinite series converges, then the limit is 0. Okay. So that means if you converge, the limit of the term appearing in the series must converge to 0. Okay. If the term converge to 0 doesn't imply that the series converges. Okay, let's look at one example, one very classical example here. So this is the harmonic series. Okay. Why is it called harmonics? Because these are the addition of overtones in music. Okay, so the one wavelength, half wavelength, third. Okay, so what's the limit? What's the limit n to infinity for 1 over n? 0. So does harmonic series converges? Yes or no? Don't know. We don't know. Okay, we don't know whether it converges or not. Okay, we cannot apply the test of divergence because the direction is wrong. We only have one direction, the other direction doesn't exist. In fact, this is the counterexample for the other direction. So, uh, but the series diverges. Okay, so this is exactly the counterexample for the other direction for our proposition just now. Everyone see it? This is the counterexample for the other direction, which means, okay, let me just write down. This is the counter example for statement if lim of an equals 0, then the infinite series of it converges. Okay, so this is the counterexample for this statement. So why does it converge? Why does it diverge? Okay. Why does it diverge? So what you can do is you also do the rearrange trick. So how do you rearrange this guy? Okay. Should I put more? Maybe I stop here. Okay. So one way you can do is rearrange them by the factor of 4. 4, right? Let me see. Okay. Do the wrong. Let me remove this guy. So we group them by power of 2. Okay. So group this way, group this way, and we make it smaller. Group by power of 2 up to all the way 16. Okay. So we can show that this sum is greater than a half plus 2 1/4 plus 1/8 4 1/8 and then 8 of the 1/16. Okay, so let me write here got 4, here got 2, here got 8 of them. There's 8 of them. Yeah. Okay. So why we do this? So we can form a constant series. I mean constant term half all the way. Okay. So which you get a which you get sum that grow larger and larger. And go to infinity. Okay. More precise method will come later, but this is one way to see it. Yeah. So the harmonic series is divergent. Okay. So this is a very classical result and very important to remember because we will use it again and again and again. Harmonic series is divergent. Okay. If I take square on the denominator, then the story will change. Yeah. Maybe we'll see later. If not, you'll see sometime. Okay. So harmonic series is divergent, and it is a counterexample to the test of divergence. I mean, counterexample for the other direction for test of divergence. Okay. Any questions? No. Okay. Cool. Okay. Next, we also have properties of convergent series. Last time we learned about properties of convergent sequence. So let's say we have two convergent series. Both of them converge, meaning, and C is a constant. They also specify some linear relation. First is if you multiply every term by a constant C, then it's actually equals to C times the infinite series. Okay, so meaning the limit of this series is just equal to C times the original limit. Okay, And then if you want to add up sequence, I mean the terms inside the series, then it's just converging to the limit of two infinite series respectively. Okay, so so another remark here is if a series diverges and you multiply that series with a scalar, then that series also diverge. Okay. We won't prove this, but you should use it. So let's use this as an example. Okay. So let's look at a sum of two sequence, and then we take the infinite sum. Anyone remember what's the first series here? Huh? It's the telescopic example we have last time, right? The telescopic sum example. Okay. So this is a telescopic sum example. So telescopic means collapsing. So it turns out that the term inside the sum at adjacent, they cancel out each other. And then what you left is left with the first term and the last term in the partial sum when you consider a fixed partial sum. And then have we done this? What's this? We haven't done, but what's this? Geometric series. Okay. So for both of them, do they converge? For the telescopic sum, did we show that it converged last time? Converge, right? Converge to what number? Can you recall? What's the sum, infinite sum for the telescopic example? Last Thursday. I think last Thursday. Yeah, last Thursday. What's it? Anyone? Huh? I mean, what's the sum? Sum to infinity. I mean, what's the final answer? 1/2. Okay, good. And then how about the geometric series? Sum to what number? Sorry. What's the sum to? So we can take out the 5, right? As stated in the properties or the theorem. Okay. And then what's this sum here? 1/3 over 1 minus 1/3. Which you get? 1/2. 1/2. Okay. 1/2. Is it? Is it 1/2? 1/2 times 5, is it? Okay. Okay, good. So we know that these two converge already, so we can use the theorem, and then we found that the infinite series of the difference of these two sequence is actually taking the difference of infinite series so which is 1/2 minus 1/2, which is minus 2. Okay, straightforward. Okay, so how about this? Does this diverge or converge? Diverge. Why? 1/n is diverging. So 1/n is the harmonic series. So what's this series here? You can take out the scalar, okay, and just look at the 1/n term, okay? 1/n term, remember, sum of 1/n is the harmonic series. So harmonic series diverges So C to the diverging, C multiply a divergent series is still converge. Okay. So this one is, please write out the detail. Spell out the detail yourself. By the way, if I'm talking too fast, please stop me and then ask me what you miss. Okay. So this one is divergent. Sure. Use the property of convergent series. Okay. Okay, next is similar to sequence. A finite number terms does not affect the convergence or divergence of a series. Okay, so for example, if for this sequence here, we want to find an infinite sum starting from 4. Okay. It's just equal to the infinite sum. I mean, it's not equal, but um, if we are able to show the infinite series that start from 4 convergent, then the series starting from 1 also converge, right? Because if this converge, we just add the extra 3 terms is the final limit. Make sense? Okay. Yeah. Okay. So for both sequence and series, the tail is very important. The first few number is not so, won't affect much on convergence or divergence. Okay. Yeah, this is a comment I want to make. Okay, next. Next is this integral test. So now this is not harmonic sequence, harmonic series now, because we are taking square at the denominator. Okay. So whether this is whether this converge or not. Okay. So you can have a guess whether this converge or not. So there's one approach to this question, which we regard this 1/2, 1/4 as the area. Can I say Riemann? Yeah, one of the Riemann uh, block you will see under y equals to 1/x squared. Okay? So if you pick the point 1 here, then you can form the area under this graph. And then if you pick 2, then you will form this area under the graph. So let me write it up. What's this point here? So it's 1/4. Okay. So yeah. So you have a partition of length 1. Okay. And then this height here is exactly following this term appearing in this infinite sum. Make sense? Make sense? Is it okay? Okay, 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 okay. So, okay. So let's compute what is 1 to infinity. So meaning we want to check this area under the curve on this part. So from 1 to infinity. Okay. So what's this? How to integrate 1/x squared? Okay, so maybe you need to be careful. So maybe you use the limit because you are integrating 0. So let's do this indefinite integral. What do you get? This integral here minus 1/x. Okay. So you get this, and then next you get 1. Is it 1? Yeah, 1. So okay. So minus 1/t plus 1. Okay, and then this is just 1. Okay, but you can see that actually the area under this graph compared to this square, right? It is, you have more than what you needed. You see? You see? So so the area under the curve is greater than the area covered by this rectangle. Okay. So since this big part is finite, of course the small part is also finite. Okay. So what am I getting here is so the sum from where to where? Let me see. So the sum from n minus 2 over n squared is less than 1, is less than the integral summing from 1 to x squared dx. Not that I throw away the first square here, right? Because here you go to infinity, so there's infinite area here. So we don't want to consider here, but we consider what the diminished part. Okay, so starting from 2, we can bound it by this integral, which is 2. Okay, so that means the infinite sum from 2 to infinity is bounded by 2. Okay, bounded by a finite number. Okay, so just now we said that finite term remove doesn't affect the convergence, right? Okay, so we could just add. We could just is it 2? Sorry, it's 1, right? Why no one correcting me? So it's equal to 1 here. Okay, so adding finite term doesn't affect the convergence. So we could might as well add 1 to our infinite series, which is 1 plus the thing that we showed just now, and which is less than 1 plus 1, which is 2. Okay, so the original series is sum to something that less than 2. Okay, so the infinite sum converges. Okay, following? Okay, good. All right. We also can use the same trick to show it diverge. Yeah, for example, we have this series here. So you can see that the power here decreases, right? This one becomes a half. At 1, we already know it diverges. Okay, 2, we know it converges. Now we decrease to half. Okay, so maybe I'll guess it is diverging. So how to show it is diverging? We also use the same trig integral test here. So we look at the real valued function defined by the sequence here. Okay. So why is this useful? Because these functions are really decreasing. Okay. So only when it is decreasing, you can hope for convergence. Yeah. If it is increasing, there's no hope because infinity bound everything. Okay. So if it is decreasing, you will have some hope. Okay. But in this case, we will use this integral test to show that it is actually diverging. Okay. So why we say so? Because we look at the nature of this. We first look at the nature of this integral first, and then we will decide how we compare these two. So what's the integral of this function here? What is it? What's the integral of this function? Huh? What's the integral of this? 2 times square root x. Okay. So we should get what do you get? 2t, 2 square root t minus 2, right? Dx. Okay. So if you take limit, then this guy will go to go to infinity. Okay. So far, okay. So far, okay. Okay. So since this guy go to infinity, if you try to put the series below the area of this curve, can you show anything? You cannot show anything, right? Because the area go to infinity. You put something finite below it, finite is less than infinity, so still valid. So if you can manage to put your series above the area covered by this curve, then your area is also going to infinity. Okay. So in this case, so how we interpret the series now? We also interpret it as a Riemann sum, but now instead of lower sum, we interpret as a upper sum. Okay, so we can realize every term here as a Riemann block. So you can plot the point out. So similarly, for easy setup, this partition, right, always have length 1. Okay, so meaning if it is length 1, then you just need to care about the height. Okay, so you just make sure you have the height that that's given by the term inside the series, okay, which is given by this function here, exactly given by this function. Okay, so maybe there's some question that you need to consider different partition of different length, but just make sure that when they multiply, they get the right terms you have in your series. Okay. Okay. So the argument is since let me put it here. Since the sum of 1 over square root n is greater than 1 over infinity of 1 over square root x, so the infinite sum diverges. Okay, so meaning if you want to converge, you need to bound with something finite. If you want to diverge, you need to bounded below by something infinite. Okay, makes sense? Yeah. Okay. So here is the summary here. So let's say we have a continuous positive decreasing function. Okay, because we are talking about sum, right? So we are positive. So continuous and then decreasing. Okay, so from 1 to infinity. 1 is because our series start from 1. And let an equal to fn for all positive integers n. Then the infinite series converges if and only if the improper integral is convergent. Okay. So in other words, is what we mentioned just now. So if the integral converge, then the infinite sum converge. If the integral diverge, then the infinite series diverge. Okay. But not that when it converges, right, that area under the graph is not exactly the same as the area covered by the block, right? Because this is just a Riemann lower sum. So you have some difference here. So they might converge to different number. I mean, that is usually the case. Okay, because you need to approximate very closely so that you can get everything under the graph. Okay. So second comment is not necessarily start at n equals to 1. This is what we have seen just now. We not necessarily need to start from 1 to compare the infinite sum and series, not necessarily. So here also another mentioning is f doesn't need to be always decreasing, but ultimately it have to decrease. Okay, maybe constant, and then decrease. But ultimately you cannot be constant all the way. Okay, if constant all the way, then it's not converging. So you must decrease at the end. So the idea is the tail is very important. Okay, the tail must converge. Okay, the tail. Okay, so this is the summary. Yeah, so this comment is what we said just now. It's for large n, you can show that it converge, then you just add finite term, then they converge as well. Okay, so far okay. How about do we skip this one for homework? Do we skip this? Well, you want to try? You want to try this or try? Okay, let's try this. I give you about 2 minutes and see what you can get. And then we'll discuss this one and then we'll take a break. Since this example is introduced after integral test, right? So you should start thinking from integral tests. Okay, you can keep going or I can start discussion also. So actually up to now, right, it seems that the real value version of the I cannot say sequence, but if you make the look at the real value function that defined by the sequence formula, okay, meaning you put in real value as the input, and then you see it as a function. It seems that uh, quite a few information captured inside this function, right? So we can find the limit first of all, okay, and we also can determine whether it converge or diverge. For series, I mean, for sequence we can find the limit, right? That's the first thing we learn. So, yeah. So just be aware on the real value function defined by this sequence here, this sequence or series, okay? Because in the end, sequence is just discrete version of a function. Okay, you just care about natural number instead of real numbers. So to use the integral test, right, you need to start with a function that is continuous, positive, and decreasing. Okay. So if I define my function x1 over x squared plus 1, is it continuous? Is it continuous? Continuous, right? So it is not continuous at x squared plus 1, x squared plus 1 equals 0. But when is it x squared plus 1 equals 0? Huh? What? Say again. Can be 0. Okay. So I mean, in real, it can be 0. If in complex, it can be 0. Okay. It lives in complex plane. So, since square plus 1 is not 0, and then f is a composite of continuous function. So f is continuous. Okay, so x is continuous, x squared is continuous, x squared plus 1 is continuous, and 1 over x squared plus 1 is continuous on the codomain of x squared plus 1. So is it positive? It is positive, right? Because s squared plus 1 is always positive. Because s squared is always positive. So positive plus 1 still positive. 1 over positive number is still positive. So I just write s squared plus 1 and 0, 9, 0. Decreasing? How about decreasing? How to check? Huh? How to check decreasing? F prime. Okay, you look at the gradient. So how to what gradient can tell you? Okay, if it is less than 0, then it is decreasing. So what's the f prime here? Minus 2x over s squared plus 1. Okay, so you want to make sure this is always less than 0. So when is it less than 0? From 1 to 4, 1x in 1 to infinity. Okay. Is it true for the other number? 0. Okay, 0 is 0. Okay. Okay. We also need k starting from 1 because our term also start from 1. Okay. Right. So what's next? So now we can use our test here. So if the integral, okay, if the integral from 1 to infinity is convergent, then the infinite series from 1 is also convergent. If that integral diverge, then also diverge. Okay, so how do you integrate this integral here? Okay, so what do you get? I think this one is using trigo, is it? Yeah, okay. So maybe we just skip it. Anyone manage to compute or not? Tangent inverse. Okay. So x. So I just plug in all the values. Get tangent inverse t minus pi over 4, which is when tangent go into infinity, what's the point? What's the asymptote? Pi over 2 pi over 4, which is pi over 4. Okay, so this means the integral converges. So by integral test, the infinite sum converge. Okay, Any question? No? If not, then let's take a break until 3:04. We'll come back at 3:04.
Is an if statement or if and only?
No, if
Because it's one if and only.
Oh,
If and only.
yeah, correct. Because okay, so P if and only if Q. So let me see. You're asking about this. Okay, let me just think a little bit. So let me see. So if this converge, then this one is this direction here. Okay, yeah, correct. Because the other direction actually is the contrapositive of this. So that's mean these two combined become this. So this is the contrapositive for okay. This right. This is this direction. Okay. For this direction, if you take contrapositive, become this segment here. So these two combined become this thing. Yeah.
So we cannot use this to imply this one. You know that.
Can. But normally we for at least for this chapter we care about this number here. So that's why we want to find condition again. But let's say if you happen you want to find something here and then you know about something here, then you can use this continuous.
Why this will change?
Okay. Because when we do the change of variable, right? We only fix to. We need to make sure the tangent is invertible. So I mean, we. So okay. So when we do this change of variable, right?
Okay.
Actually, we fix the domain into where tangent is injected.
Just one circle. In a fixed part. Right. Just because this is this is like the this.
Yeah,
So we needed to fix it in this.
Yes.
one part.
Yes.
Thanks.
Yeah. Any part. Yeah. Cancel. 很多，你想全部都要看？
没有就是我会调一下。
OK。 可能
太不近
我可以看一个先啊，
太不近
其他 office 好不来了。
太不见还是太不见的就真，而且表示
零是 infinitive。哦，
我记得写等于太不见就可以了，是
等一下，等一下，哎，对，你知道你要什么？知道你要用什么？你知道你要用什么？
嗯，
你知道你在用什么？就是你把上面下面都看成 conversion sequence 先嘛，对不对？
嗯，
上面 conversion 很简单，因为它是 constant。下面为什么 conversion？对，为什么 conversion？
嗯，不能
但是我们 limit 可以随便，I mean，因为 function 的时候你就可以带 limit 进去，因为它是 continuous function。但是如果是 sequence，你不可以带 limit 进去 square root。我们没有一个 rule 是在 sequence 的时候可以带 limit 进去。我们就呀，所以如果你要带 limit 进到 square root 里面，就要从 real value 来去看。对，意思说e over n 是continuous，4 over n cube 是 continuous，加起来 continuous，square root 又是 continuous，所以我就可以 consider limit on real value function 哦。但是 limit on real value function 你知道吗？这个东西是零嘛？所以因为我们有一个那个 theorem 说，如果我知道 real value function theorem 的 limit 的话，我就知道 sequence 的 limit 哦，所以我的 sequence limit 也是零，所以现在应该是 e over 零就可以那个了。因为 continuous 呀，所以如果这边只是 sequence 的话，你是不可以这样带进去。嗯，
因为哦，
对
不 correspond 的
对，
很顺便接在一起了，
所以你没有，你要知道你在哪一个，我在哪一个世界里面，你是在 sequence 里面还是你在 function 里面？但是我们有一条桥 between function 跟 sequence。现在，如果我们可以解到 function，我们就可以解到 sequence。
全部我就找回太不见，
嗯，这个啊这个啊，对呀，对，是说 divergent。可以，我可以找一个 subsequent 是 divergent 啊，那时候它里面一定有一根接一根接一根接一根接，所以它，我觉得可以这样子。所以它的那个里面它有很多一根接一，你看得出吗？看得出啊？OK，你看得出的话，你就说，嗯，就是说一根减一不能够同时 convert 去一个号码。其实我们要说 diverge 的时候，这个其实是 limit 的这件事，
嗯，
所以应该怎么说嘞？这个的理由就有点像我们说那个一跟减一没有，我也没有什么怎么说啊，我们只是看吧。如果它大概 exist，就是如果要 rigorous 一点讲，就是说你假设它是 convert 去一个 limit，但是一跟减一不可能 convert 去一个 limit，因为你不能够
就是
一跟一啊，
explanation
不用 我觉得这一堂这一课不需要 explain 那些东西，这一课你可能只要说啊，你就说里面有一跟减一的 alternating 的 sequence，那它就 limit doesn't exist.
Okay.
如果真正要说的话，你要说，因为1跟减1有距离，那它 different by 2，你不能 make 那个 arbitrary close to 个 limit。如果你如果 make 那个 limit arbitrary close to 1，它就会离减1很远了。如果你 make 它 arbitrary close to 减1，这样就离1很远。那个是真正要讲的，但是应该是不用在这堂课。
Yeah.
Hello, testing. Okay, let's pass this down and then we will start. And by the way, who is Ryan Tan? Is Ryan Tan here? Not here. Hey, you asked quite a few things on Teams. Ryan Tan, Hu Xiang. Is it in this class? Let me see. Ryan Tan, Hu Xiang. Not in this class or. Go. MAT, yeah. Not here. Ryan Tan, Hu Xiang. Not your friend. None of his friend. None of you is his friend. Okay. Huang Xueyan, is it you? Not you. Huang Xueyan. Oh, Xueyan. Okay. Nice to meet you. Okay. Next. So next, we'll talk another important series, which is P series. So just now you already encountered few of these. So when P equals to 1, it is the harmonic series. Cannot see anything. Wait. Okay. So when P equals to 1, it is the harmonic series. And then when P equals to 2, you see that this thing converge. When P is 1/2, this thing diverge. Okay. So in general, we will show that P series converge if and only if P is strictly greater than 1. Okay. Strictly greater than 1, it converge. Less than 1, then it diverge. Okay. Okay. So what should we do first? So there are two directions here. So one is if it converge, then P greater than 1. Or the other direction is if P greater than 1, then it converge. Okay. Maybe, how should we start? Maybe we can start P greater than 1 first. So from left, from right to left. Right to left. Okay. So I want to show something convergent. Okay, something convergent. So we have the two, which is the integral test. Okay. So you need to check. So now we define fx to be 1 over np. So you need to check that this is actually continuous, positive, and decreasing. Okay, I leave you to check it. It is, but I leave you to check it. So please check. Okay. So in assignment, you should check, right? So check. Okay. In assignment, you should check. Okay, and then so let's look at the integral of this thing. Over np. So what's this integral here? Okay. Let's do a quick integration. So if you cannot follow, maybe you need to believe me. Okay, so this is the integral you got. So there's some weird synchronized variable. So change it to x. So we are looking at the real value function. So if you see me swapping between x and n, right? So I'm swapping between discrete and real. Okay. So when I talk about real, I put x. If I talk about sequence discrete, I put n. So what's this? So what's this thing here? If you can compute on the spot, I think you will get something like this. -1. Is it correct? I hope it's correct. Okay, so this thing, this piece here. So when does this finite? When does this finite? So we start with p greater than 1, right? For now. So suppose p greater than 1. Okay. So let's start from 1 point. P greater than 1. If p greater than 1, okay, so this thing is finite. And p greater than 1, this is some positive power of t. Right? Okay. So this is a finite number for some positive number here. So if you take t to infinity, then this term will disappear. Okay, so you're left with -1. So it's just equal to -1 or 1 or just p minus 1. Okay, which is finite. Okay, so since so by the integral test, since the integral converges our infinite series also converge. Converge. Okay. So far, okay. Okay. So how about the other direction? Okay. So the other direction says that if p series converge, then p greater than 1. Okay. So instead of doing this, we can prove the contra positive. So meaning if p is less than equal to 1, then the p series diverges. Okay. Instead of showing the direct proof, we show the contra positive. So the other direction is if p is less than equal to 1, then p series diverges. Is diverges. Okay. Okay, so at p equal to 1 already shown is the harmonic series, right? Okay, agree? Okay. So what's next? So p equals to 1 diverge as harmonic series. Okay. So how about p that is greater than 0 up to 1? Okay. And maybe we can look back again on this integral here. So let's bring the integral back to work. See if we can see something useful. Okay, so let's say my p is in between 0 and 1. Okay. What happens here? Here is still some finite number. Okay, so the scalar here is still finite. How about the power here? Since it is less than 1, right? So when you take -1, you become a negative number. So this t will move to the numerator. And then you take t to infinity, you get infinite. Okay, so this one actually go to infinity. Okay, so by integral test again, since the integral diverges, the infinite sum also diverge. Okay, so this one is a by integral test. The other direction of integral test, if the integral diverges, then the series diverge. And the series diverge. Series diverge. Okay. Okay, so why I split out p equals to 0? So if p equals 0, right? So this term here is really, what is it? It's just, what's that? It's just sum of infinitely many 1. Okay. So if it's sum of 1, does it diverge? Diverge? No, no one. Infinitely many 1 doesn't diverge. Diverge, right? Why? So diverge. Why diverge? What test can you use? What test can you use? Divergent test. Good. So by divergent test, so you look at the limit of each term. The limit of each term is actually 1, which is not 0. So imply the series diverge. Okay, so how about less than 0? So if I compute less than 0, then like we will finish. We will be done. Okay, so use the divergent test again. Okay, we expect it diverge, so we expect this guy go to something not 0. Okay, so what's this guy? This is the infinity of n to the p, which is infinity, which is not 0. So by divergent test again, this series actually diverge. Spell division. Okay. So I got a team message. They say I don't know how to solve this. I don't know how to solve that. Okay. So don't try to how to say? Don't try to fix yourself into a box. You know what I mean? So don't try to try to think from first principle. Okay. Always try to think from first principle first. Okay. Use the easiest tool first. Okay. So start from the first thing that I taught you how to find the limit. Okay. So you should start from the real value first, and then see if you can use that to solve that question. If not, then you use another properties, and then you use the next theorem, and then getting advanced. Okay. Don't straight away want to try something like what did we learn last time? Monotone, for example, monotone sequence theorem. Okay, you want to use that, for example. Okay, sometimes it will be overkill. Okay, you don't need to do that much work, but maybe you can do it as well, but you just wasting time. Okay, so try to think from first principle first. Don't try to do fancy stuff. Okay, yeah, this is one of the advice. Okay, so one example on this P series here. So we already know that only P greater than 1, this series converge. So can you determine whether this series converge or not? Yes or no? Yes, okay, because 1, 0. So since 1.001 greater than 1 by P series, and this converge. Okay, so actually this result is very useful, so make sure you also remember. So now we already come across a few classical results, so make sure you will remember and then use it. Okay, And then, okay, this one use integral test. So this one I just left as homework. So we won't pursue again. Okay, do at home. So next. So next, now we want to estimate the error terms. Okay, so let's say our infinite series converges. Okay, and have a sum. Okay, we can approximate Sn. You can imagine that our Sn keep converging to that number. If you add more n, then you'll be closer to that number, right? Supposingly, because if you reach a limit, then you need to approach your limit every time you add the terms. Is it clear? Clear? Okay. So in your mind, you should have, okay. For example, just now I give you a convergent sequence, right? Okay, this one converge to 3. So you can see that. What's the difference between 1/4 and 1/3? Okay, what's the difference between 1/4 plus 1/16 and 1/3? So you're getting closer to your target, to your limit. Okay. So now we want to estimate. How to estimate? So to estimate the remainder, we can use integral tests. Okay, using the upper and lower bound, upper sum and lower sum. Okay. So again, because it's an integral test, we need to start with the same condition, continuous, positive, and decreasing function from interval 1 to infinity. And then the sequence defined by this function, look at the sequence defined by this function, the discrete function, in other words. So if the infinite sum is known to be convergent, okay, if we converge, and Rn is the remainder after you taking away the n partial sum, okay, then we can estimate this remainder here. Right, because remainder is still some infinite terms. Correct? If you take away finitely many n terms, you still have infinite terms. But these infinite terms, they add up to smaller and smaller number when you take n go to infinity. Make sense? Okay. Okay. So how to estimate them? So it's estimate bounded below by the integral of n plus 1 to infinity and bounded above by n to infinity. So you should observe that this guy here has smaller area than the left guy have the smaller area than the right guy. Because for the right one, you start from n. Okay, so one start from n, one start from n plus 1. Make sense? Okay, and also your curve is decreasing. Okay, so you get rid of this part and start from this. Okay, so diagrammatically, it is like this. So if you are integrating from n to infinity, is this diagram here, and then n plus 1 to infinity is that diagram. Okay, so for example, how are we gonna use this? So let's look at this example here. So we want to find an upper bound of the error in the first 10 term using the sum of the first 10 terms to approximate the sum. Okay, so meaning, okay, so this series, right, is what series? What kind of series is this? P series. Yeah. I just want to confirm something. Okay, yeah, right. Yeah, so this is a P series, and this is P equal to 3. So 3 is greater than 1. So this is converging. Okay, so converging meaning it is equal to some number. Okay, some unknown number for now. Some unknown number. So we want to find this number. Let's say we don't have sophisticated mechanism to find. So we just add the first 10 terms. So let's see what's this. How close is this number to the final answer, right? So we want to see what's the upper bound for the error. So let's say we add up to 10 terms already. Okay, we add up to 10. Right. So this is our S10. Okay. So how close is S10 to S? Right. S10 will converge to X. Not converge. Yeah. A bit weird if I write like this. So you will go to X. Okay. So how far is this from X? Right. Maybe you don't have calculator, you don't want to do this. So let's use R10. Right. So R10 is what? R10 is equal to R10 is equal to X minus X10. Okay. So by this theorem here, we can bound this by an integral. Right. So from where to where? From 10 to infinity. Dx maybe change to X. Real number. Okay. So this maybe it's easier to do calculation. Okay. Can you quickly see what's this integral here? Check if this is correct or not. Okay. So integrate to 1 over 2x squared minus, so which is 1 over 200 minus, okay, you like, maybe I move this to the back. Maybe dt 1 over 2t squared, which is 0.005. Okay, so it means that if you sum up to 10, it is 0.005 away from your at least, not at least, maximum 0.005 away from your sum. Okay. Actually, this sum, if you go and search, right, Wikipedia or somewhere, this sum is actually a Perry sum, Perry constant. Okay, a lot of this sum is quite interesting. They sum to the number involving pi. Okay, yeah. So if you want to write an exposition about this interesting infinite sum, you also can write, because I think they are quite applicable in some field. Yeah, real life field. Okay. If you want to search for it and then you want to write something interesting on it, also can. So maybe it's your project question. Okay, so next question is, if I give you another condition, let's say I want to approximate closer to my x, okay? Which n should I take, okay? With error no more than 0.005. Okay. So I want to be as 0.005 as close to my final answer. So I need to bound my error term by 0.0005. Okay. So just now, what's the integral we get? So the integral we get just now is 1 over 2, 2n squared. Okay, so this is 1 over 2n squared. Okay, so we want to make sure that this is bound by 0.0005. Okay, so to do this, you just move around and then you will find that it is actually greater than 31.623. Okay, so this means your n need to be at least 32. So we need to sum up to 32 terms to make sure the error is no more than 0.000. Okay. Yeah. Any problem? Okay. So depend on how the question is asked, you need to use that relation between the error term and the integral term. Okay, so what's next? Next, So since we have the relation between remainder term and we have the, okay, let's write what we have. So Rn, go into vector space. Rn is less than the integral from n to infinity and greater than or equal to the integral from n plus 1 to infinity. Okay. Then if we add the finite partial sum to all of them, then we will get the following identity, right? Because Sn plus Rn is exactly the whole or the whole series, yeah, infinite series. Okay. Because Sn plus Rn is just x, right? And it's just something left over when you take Sn away from x. Okay, make sense? So let me write Rn is equal by definition x minus xn. Okay. Yeah. Okay. So what does this mean? So how is this useful? Use the above inequality with n equals to 10 to estimate 1 over n cubed. Okay. So what's this asking here? So this is saying that if you check n equals to 10, if you add up to n equals to 10, the infinite series sum, can you find bound on infinite series? Okay. So what do I want to do? Actually, what I want to do is I want to bound my sum, okay, in between the n partial sum. Okay. So n partial sum. So this is what I'm doing. Fx, yeah, fx, fx, both f over x. Okay. So we will skip the middle step. You can verify at home. We will look at the result and then see what's going on. So meaning you need to compute what is S10. So you need to compute A1 plus A2 plus A3 plus dot 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 out to N. Okay. And then you need to compute the integral. And then you will get something like 1.664 less than equal to this. Less than equal to 1.202532, something like this. Okay. So you can see that your sum is around 1.20. Okay. And then in between. So if you can imagine that if you take more terms, so these two guys will get as closer as possible together. Okay. As closer as together. And then, yeah, so you will see that this number lie between 1.20 something. But this actually is not much enlightening. So more enlightening is, can you find an exact form for this answer? As what I said just now, maybe you can find it in terms of pi, in terms of e, in terms of some irrational number, or it is just a rational number. Okay, but when you can't do that, then this answer maybe is some good choice. This is some of the numerical people doing. They keep estimating number. But if you can find the exact form, I think will be better. Okay. Yeah. Okay. So next. So next is the so what we have learned integral test, and then use integral test to bound remainder, and then to estimate our sum. Next, we will use comparison test. We'll introduce comparison test. One of them is direct comparison test. So if you have two sequence, okay, and then bounded similarly, one bound the other one. So let's say, for example, AN is bounded by BN, okay, but both of them are positive, okay. Positive is very important here. Later, we will deal with something negative, but now let's deal with all positive sequence first. And then if you consider the infinite series of BN, if it diverge, if it converge, then AN converge. If AN diverge, Bn diverge as well. So this is exactly the same. Can I say exactly the same? Similar to the integral test. Okay. So, but this is a discrete version. So if you think of it, An is like this. Okay. And then Bn is something higher. Okay. So this is a discrete form. Just now we have continuous form. Now it's a discrete form. So if Bn, this is Bn, this is N. So if Bn, if you sum over all of them, converge, so it's finite, so the area is finite, then the sum of An also finite because it's you bound by a finite number. So if An, when you sum this guy, go to infinity, is infinite, diverge, then Bn also sum to infinity. Okay, also diverge. Make sense? Okay. Else, should I prove this? Maybe I don't want to prove this then. Okay, I want to prove this. Maybe I'll write inside the note if needed. The idea is what I said just now. Okay, so meaning we need to compare, right? So we need to compare some sequence here. So we need to compare to something that we know. Okay, what we know? We know P series. When does P series converges or diverges? We know. We also know about geometry series when converge, when diverge. So it's best that you can start comparing series to these two series. Okay, to what we know. So always what we do is start from what we know. Okay, and then slowly we'll learn new stuff. Okay, I want to prove it. So let's go into example. Okay, so determine whether this series converge or diverge. Let you think a bit. Whether this converge or diverge. Let you try it for 3 minutes and discuss with your friends. Whether this diverge or converge. If you want to show that it is converged, then you need to bound by something that is converging. If you want to show that this diverge, you need to bound below by something that is diverging. So which one you want to do? Start with the series that you know, see whether you can bound this on the bounded below or bounded above. Anyone got any idea yet? Does it converge or diverge? Converge. Okay, what have you tried? Huh? What have you tried? What's bigger than it? So what's converge? What is the convergent sequence that you pick, which is convergent? Okay, good. So what's your name again? Wensu. Okay, Wensu, huh? Wensu. Wensu. Okay, Wensu. So Wensuo suggests that we have this inequality here. Does everyone agree we have this inequality here? Because the denominator, when you decrease, right? So the fraction will increase, right? So this is one of the classical calculus or analysis trick to get rid of the smaller number power terms. Okay, so these terms are positive, right? So you can just take this away and then make this become smaller, then the whole term will become greater. So you have these inequalities. If you don't buy this argument, you can just multiply out and see that actually this inequality is satisfied. Okay, there's several ways you can check it. So we have this inequality here. Okay, but we know that the series defined by the sequence on the left, okay, is actually a P series. Okay, but it is not directly P series yet, right? So we need to take away the scalar first, and then we'll see that it is a P series with P equals to 2. 2 is greater than 1. So by P series, this is converge as a P series as since P equals to 2, which is greater than 1. Okay, so if I want to be pedantic, right, here I need to use the property of convergent series. Okay, so if it's a good practice that you write everything down, but when you go beyond, then this thing can keep behind your mind, and then you can just ignore it. I mean, don't write it down, but you have to keep it in your mind. Okay, yeah, make sure you know that something is going on here. Okay, so since the right series defined by the right sequence converges, so the series defined by the left sequence also converge. So by the direct comparison test, comparison test, the left series converges. Okay, good. How about next one? Can you quickly decide whether this is converging or diverging? Converge or diverge? Huh? Say again? Diverge. Why? So ln n over n is greater than 1 over n. Okay. So 1 over n is a harmonic series diverges. So the series defined by the right sequence also diverge. Okay. So so please write it up. Okay. By simple comparison to harmonic series. Okay. Okay. Yeah. Oh, you mean long one, huh? Yeah. I mean, okay. So you mean like this? Wait. Let me think. Where is long n equal to 1? Long n equals to 1. Are you talking about this problem here? When is long n equal to 1? Equals to e. Okay, equals to e. So when what is e? 2.7 something. Huh? Is it 2.7 something? So so this inequality will hold starting n greater or equal to 3. Is it? Okay. So yeah. Okay. So this means precisely is when n starting to 3, you get this divergent, but we don't care about finite term, right? So you can add the finite term in, but still diverge. Infinity plus 3 finite numbers still diverge. two. Okay. Yeah, good. So make sure you need to check when this thing this is actually quite important. Yeah, quite important. I write it out in full for this question yourself. Okay, so next. So this is a new test. So just now it's just a simple comparison test. So for the limit test, if you don't know how to compare AN and BN, okay, that's fine. You can take their ratio, okay. If this ratio turns out to be something finite, they either converge together or diverge together. Okay? If this limit turn out to be 0, and you know that the thing in the denominator converges, then AN converges as well. Okay, because if talk more, so you need to make sure that the thing that you divide is always positive. Okay, you don't want to divide by something negative, something 0. Okay, otherwise you get infinity. Okay. Okay, so I don't want to pursue with the proof. Maybe I'll write it down if you want to have a look. So let's see how to use this. So you look at the ratio between AN and BN. If this L is finite number, is some finite number, that means the infinite series defined by both sequence converge or diverge together. Okay, if you happen to know one of them converge, then the other converge. One of them diverge, the other diverge. If L is 0 and the series defined by the denominator sequence converges, then the numerator series converge. Okay, right. So let's look at this example here. Okay, so I'll let you try. Let's try see if you can use this theorem to show this. See if you can cook up some AN and BN to see whether this sequence converge. Let you think for a few minutes first, and then try if you can work something out. So to use the, what do we call it again? These limit comparison test, right? So you also need to start with some sequence that you know whether it is converging or diverging first, right? And then use it to compare to this sequence here. And start with something that you know first. It's okay if you don't get it, but try, see if you can cook out something. Okay. Yeah, this the most important thing is you try first. Okay. Okay, time's up. Let's see. Does anyone has any idea? Or if not, you want to guess whether it's converge or diverge? Anyone have any idea? Want to have a guess? This converge or diverge? Converge. Okay. Did you try anything yet? Have you managed to try anything? Okay. Want to modify this term first, is it? N cube. Want to modify this by n cube. Okay. I'm not sure why, but maybe we can try. So we get 3 over n squared minus 2 over n cubed over 1 plus 2 over n plus. And then what do we want to do? Top is an, bottom is bn. Okay. I just follow what you do. Let's see what will be happening. Yeah. Then the limit of the ratio. Okay, sure. So this is what? 0, right? Okay, so what does this imply? Okay, so let's say if Bn converges, then An converges. Okay, sure. So does Bn converges? Bn converge? Okay, so An converge. Let me see. Does Bn converge? Bn doesn't converge, right? I mean converge, not the sequence converge, right? It's the series converge. Right? So be careful. Is this one need to be converging? Need Bn, the infinite series be convergent. Okay. Right. Right. So if you take the limit of Bn, right, it is 1. So it diverges. Even though Bn diverges, even if I have the infinite series of Bn converging, I got that An converging. It doesn't really tell me much about the original sequence here. Right? Because An is not distinct. Okay, so we are interested in this fraction here. Okay, so this is a thing I want to warn you. Don't just do for the sake of doing. Okay, so you need to know what you are doing. Okay, I mean everyone will make this mistake, but you need to realize it. So this doesn't quite work. So what we interested is the whole fraction here. Okay, it's the whole sequence here, right? So let's make this sequence into our AN. But by the way, thank you for the answer. Okay, so we're interested in this one. Okay, so what BN can we pick? We can, yeah, we can start guessing whether it is convergent or divergent. Then this will affect what BN we're going to pick. Okay, let's say we assume that it is converging. Okay, so we try to compare with a convergent series, see it works or not. Okay, so of course I know the answer, but just give a rough idea. So let's say we have this Bn here. Okay, this Bn here is a P series, right? So this Bn is a P series, and then what else? So it's converging in particular because 2 is greater than 1. So if I were to show that An converges, either the limit is 0, either the limit is something finite. Okay, this is 2 goals I want. If I want to show that it is converging. Okay, so let's see we have these 2 goals. These 2 goals. Okay, so let's compute the limit An over Bn. Okay, so what's this? Okay, what does this simplify to? So this simplified to 3n cubed minus 2n squared over 3 times n cubed minus 6 times m squared plus 3, right? Okay, so I think up to this stage we should know what to do. So we can cancel n cubed now. Okay. And divide both sides with n cubed. Okay. So now these are combination of convergent sequence. Okay. So I can bring my limit into each term, right? Which I get 3/3, which is 1, which is something finite. So by the limit comparison theorem, my AN converges. Sorry, my infinite series converges. Okay. So by the limit isn't yes. My limit comparison test, my limit, yeah. So the infinite sum converges. Okay. So so how do I come up with these 3/n², right? Okay. So like what we mentioned just now, okay. For this kind of sequence, right? One tips is you don't care about the smaller, don't really care about the smaller degree terms, okay? Because the leading degree will very much affect your terms, how the terms grow, okay? So let's say this two leading term is 3n and n cubed, okay? This leading term will what? Will simplify to 3/n². Okay, so this is how the idea of 3/n² comes up. Okay, so always look for the leading terms, okay? The highest degree term. Okay, the highest degree terms will pretty much lead how fast this number grows. Okay. Okay, let me see. Okay, so let's take a break, but in the break, maybe you can think about this question. Then later we will talk about this question, then go to the next section. Okay, so we will resume at 4:07. Is the attendance list done yet? Where's the attendance list? Where's the attendance done? Okay.
Theorem, sequence theorem. If a function, if a sequence is between sequence 1, sequence 2,
Okay.
and sequence 1, sequence 2 are convergent.
What? Convergent,
They are convergent. So the sequence is not convergent.
You sure?
So if I use this in
Hey, wait. Oh, right. No.
Oh,
No. I can. Huh? No.
The convergent number is you.
Huh?
So
No. I mean, if you are bound by two convergent sequence, doesn't mean that this sequence converge.
Was currently
You mean like the squeeze theorem?
Yeah.
Okay.
So if I use the theorem in series, so this means that the series 1 and series 2 are convergent. And I have a series between series 1 and series 2. So whether cannot get the conclusion of the series is convergent.
What's your question? What's your question? Can you say your question first?
The series and
The what? Sequence? Series.
the
Okay, series.
series and series are both convergent.
The series are convergent. Okay. The series are I think. Okay, so you're talking about the partial sum are converging, right? When series converge, that means the partial sum converge. And then?
And the other series between.
So the partial sum is between, okay.
So whether should I guess the series convergent?
What? Where do you get the series converge?
Yeah.
What
Oh,
do you mean? So you got a series. Okay, so you got another partial sum from another series that is bounded by two converging partial sum. Is that what I mean?
Yeah.
Okay, and then the question is, when do you see the bounded bounded? Okay. Let me. Okay. So let me back out of it. So mean by when? I thought squeeze theorem already told you.
Yeah.
If it's bounded, then sequence converge. So what do you want?
No.
Huh?
There is a series with I don't know the series is convergent or divergent or converge.
But I thought you say you start with. Okay, let me write out what you say. So this one n x. Can I write? So this is n. So this is n. Okay, so this one n is I think how to say. So this one converge to L. This one converge to L.
Yeah.
Right.
Yeah.
But squeeze theorem told you that this also converge to L.
That is the sequence will be equal to 0. The converge to 0.
This one converge to 0.
Yeah.
This
and
one
the also converge to 0.
to 0.
Yeah. And
this one converge to 0 as well. By
yeah.
squeeze theorem.
Yeah, but the sequence of Bn, but the series of Bn is converged, and the series of Bn is also converged.
Wait. So this Bn is a partial sum or just the term inside your sequence?
Yeah.
So it's just term inside your sequence.
Yeah.
Okay, so meaning, okay, so you have this, right?
Yeah.
And then you know that Bn is very equal to and then this one converge, this one go to 0. Okay,
Yeah.
so these two go to 0 implies that these two converge, right?
Yeah.
Okay, so how to say? So they might converge to different number.
Yeah.
Right. So maybe converge to L1 and converge to L2. Okay.
Mm.
But you know that this is greater than equal to this one. So in particular, we should know that. Okay, since these two converge to 0, this means that this one also converge to 0 by squeeze theorem. Okay.
Yeah.
Squeeze theorem. So this means this guy also converge. Okay, by this one. Okay, L3. Okay, so now you converge. Are you happy with this, or you want to see this, or what? So this guy converge. Is this what you want to ask?
Converge.
Converge.
So this theorem can use in example. 好，apply
No.
no.
Unless I ask you done. Unless I already asked you to prove in the assignment, then you can use. Or I present in the lecture, then you can use. Or we have discussed in the class, then you can use. But not for now.
Oh.
Yeah. I mean, it's worth to write it down if you want. You can write it down, the details. And then you can let me check if you want. Yeah. I mean, it's worth to write it down. Actually, there's something non-trivial here. So if is it? So there's something non-trivial here. So okay, if you don't care about how you relate this L1, L3, L2, basically this is done. So CN is converging. But if you can extend this result further, you can probably show that L1 is greater or equal to L3 and then greater or equal to. But if you don't care about this, I think this is what you want. Yeah. Okay.
Can I use the team project?
You try and write it out first. You write it out first and then see how it goes.
Thank you.
Because I think it's not too much work, I guess. You write it out first, and then you let me see. And then I will suggest something. Yeah. Okay. Yeah. You write it out first and then, or maybe you can collect a few lemma, like new lemma that you wanted to prove, also can. Maybe one of them is not enough. You can prove a few of them, then it's okay. Yeah. So you can think of some easy question or simple question. I mean, not easy, simple, that we can be solved what we learned. If cannot be solved with what we learned, then maybe you need to put some new definition in, and then we can solve it. Okay. Hello. Testing. Okay, so has anyone tried this? I mean, you can take rest if you want, but if you have tried during your rest, but let me know if you have tried. Anyone try on this question? No one tried. It's okay if no one tried. I will show it. So, like what I said just now, right? So the leading degree terms will be pretty much determine the behavior of this sequence. So what's the leading term here? 1 over n. Okay. So we can compare to 1 over n. So be aware that Bn is what? 1 over n is what? If you consider the series. P series, yeah, it is a P series, one of the P series. In particular, it is the harmonic series. Okay. So it's diverging. Okay. So meaning you are comparing to something diverge. Okay? So if the limit is finite, if I compare n, bn is finite, then they diverge together. Second one, you cannot use, right? Because if L equals 0 and B diverge, there's no statement about this. Okay, so we only can n for the first one. So let's n for the first one. So let's take our B. So let an be the original sequence, and bn be the harmonic series term, yeah, sequence. So let's compute the ratio an over bn. which is equal to what? N over square root n squared plus 19. Okay. So what can you do? You can do a trick. Okay, divide by 1 over n, where you get 1 over square root 1 plus what? 19 over 19 n squared. Okay. So what's this? 1. 1 over 1. How do you compute 1 over 1? Yeah. Oh, okay. So you bring the limit into the square root, right? Can you bring limit into square root or not? Huh? If it is real value function, you can. If it is sequence, you cannot. Okay. So you need to start with real value function. Yeah. And then show that this limit, sorry, just look at this 1 plus 19n squared, s squared. Okay. This converge to 1. So imply the sequence converge to 1. So then you can get 1 over 1. Okay. So for sequence, we cannot simply bring limit into square root. So you can do it for real value function first. And then we have the theorem say that if you can compute the limit for real value function, you also can compute for sequence. Yeah, use that. So this is 1. So this is finite. Hence, by the limit comparison test, limit comparison test, the series diverges. Oh, good. Okay. Any question? Any question? So this is a very technical part. Don't simply bring limit into something. Ask yourself whether this is a convergent sequence or not. Okay. Unless you know that a square root of this thing is converging, then you can use it. So meaning you already passed through this stage here, then you can bring the limit. But anyway. Yeah. Okay. So next one I will left as a homework. So you can try this. Try and find your favorite BN. See if you can show this diverge or converge. Okay, so what time? 413. Next. Okay, next. Alternating series and absolute convergence. So now we look at a particular series which is called alternating series. So it's a plus minus popping in front of the scalar. I mean the sequence. Okay. So when is this kind of sequence converging? So we give a criteria here. There are 2 criteria here. Okay. So first of all, Bn is greater than Bn plus 1. So that means it is decreasing. First of all, we look at decreasing alternating series when you just looking at Bn. Okay. So regardless what is the sign in front of them, you look at the modulus of that term. And then the same condition we have, if the limit of Bn go to 0, then the series is convergent. Yeah. Okay. So there's one diagram you can draw here. So you have B1, okay, but B2 is less than B1, and then you take the minus, so you take the difference away, okay, and then you add B3 again, which is smaller, and then take away B4, B5, B6, then keep going on until you get 0. Okay. Okay, so your sum will be this occurring at the center here, about the center. depend on your B, is in the middle here. Okay, so first is S1, and then S2, S3, S4, S5, S6. You got a zigzag-like behavior, and then you stop at X because the limit of Bn is 0. Okay. So one thing to note here is if you take your final sum, let's say it converges, and then take away the n partial sum, okay, and then look at the difference. Okay, we only care about modulus, so we care about difference. I don't care is s greater than Sn or Sn is greater than x. Okay, it is possible that Sn is greater than x. Okay, you can see from this example here. It is possible that Sn will be greater than x, but if you go to the next term, it will be strictly less than x again, and then bigger than x, and then strictly less than x, and then bigger than x, and then keep going forward and backward. Okay, until you reach x. But anyway, it will be always, the difference is always less than or equal to Bn plus 1. Okay. You can show this if you are interested. We won't do this in class. Sometimes this is kind of important or useful. Yeah. Okay. So if you are interested in some proof, right, but you read about it, but you are unsure, you can come to my office hour and ask me about it. Okay. Because some proof is tedious and not useful, not used in the class, I won't do it. Okay. I'll do those proof that is useful in the class. You can use it in assignment, or maybe I can test you in the test. So I will do it in the class. Okay. Next, show that alternating harmonic series is convergent. Okay. So this is a harmonic series, but we add in the factor of alternating minus 1. Okay. So we want to show this is convergent. Okay. So just now, what did we learn? So we need to make sure that Bn is greater than Bn plus 1 forever, and the limit of Bn is greater than, the limit of Bn is actually 0. So there are two conditions to check. Let me write out. So Bn greater or equal to Bn plus 1 for all n. Okay. 2, limit of n infinity Bn equals 0. Okay, one thing to note here, right? Actually, I can throw this. Okay, I cannot throw this, but you can see that you cannot have equal sign forever due to this condition here. So this limit to 0 help you to decrease that function ultimately. Okay, this is just non-increasing. Okay, so first condition is non-increasing. Second condition is diminishing. Okay. So let's check if we have these two conditions here. So do we have the first condition? It's Bn in this case. Let Bn be 1 over n. Right. Okay. We don't care about the plus minus. We only care about the the modulus of the term in the sequence. Okay. So is it true that 1 over n greater or equal to 1 over n plus 1? Is it true? Okay. So it is true because we are divided by a larger number, and our n is running from 1 to 1, 2, 4, n 1 greater than 1, greater or equal to 1. Sorry. Okay. So, or in other words, it's actually n plus 1 greater or equal to n. Okay. Maybe this one is easier to see. Okay. How about the next one? I think the next one is easier to check. This is the first thing we think about this harmonic series. So this is actually 0. Okay. So you can see that alternating harmonic series converges, but harmonic series doesn't converge. Okay, if we add this alternating behavior into this sequence, actually the series converges. So by the alternating series test, the alternating harmonic series converges. Converges. Okay. Okay. So any question? Any question? Any question? No? Okay. Now your turn. Show this is convergent. Give you about 3 minutes. I show that this series converging. So you can see that there's an alternating behavior happening again. So yeah. So in this case, instead of considering power of n, you're considering factorial n factorial. You want finish? You want try? What's the Bn you try? Maybe I can work together. What is Bn? It's B 1 over n factorial. Okay, good. So the first condition you need to check is 1 over n, whether 1 over n factorial is greater than 1 over n plus 1 factorial, right? So this is true because n plus 1 factorial is greater than n factorial. Okay, so this implies that Bn is greater or equal to Bn plus 1. Okay. Second is you want to check the limit of infinity of your Bn. Okay, so this is obviously 0. Okay, so by alternating series test, it is convergent, or the series is convergent. Okay. Maybe try one more. Try this one. Okay, try this one. And then you let me know. Anyone try whether this converge or diverge? Diverge. Why? Say again. Why diverge? Divergent test. Okay, how you do the divergent test? You do divergent test. You limit to infinite? You sure? You also get limit to infinity. Squeeze. You want to show it diverge or converge? Diverge, how to use squeeze theorem to show something diverge? Yeah, correct. Squeeze theorem again. Okay. Okay, yeah, okay. So one way, okay. If you try converge, I think you will fail. So why will you fail? So let's look at the limit of this individual term first. Okay. So what's this limit? This limit is 1/4. Sorry, 3/4. Okay. But you need to consider the alternating version of this limit. Right. So which means -1, what happened to -1? Is either 1, -1, 1, -1, 1, -1, 1, -1. Okay. So this means the limit alternates between alternates between 3/4 and -3/4 and 3/4. So, but if you want to be precise, which we won't pursue in this course, you need to find subsequence that converge to -3/4 and subsequence that converge to 3/4. Okay. If you want to be precise. But in this case, we will see that this alternate between -3/4 and 3/4. So this means that the limit doesn't exist. Okay. So if it doesn't exist, then we can use the use what? Test of divergence. The divergence test. Okay. Test of divergence. If the series diverges. Yeah. Okay. So next, we will left as an exercise. So still considering something is converged or diverged. Let's see the next one is worth to do. See how much we have to go. Still have tomorrow or Friday. Can we do this? Do you guys want to do this? You want to do this? Yeah, let's try it and do this. So this says that they ask you to find the sum of the series correct to 3 decimal places. Okay. So which means you need to find sums n such that x minus xn is less than equal to 0.0005 at least. Okay, because you want to round up to something 3 decimal. Okay, but the first thing is you need to decide whether this x exists or not. If x is infinite, how are you gonna find this difference? Okay, so first determine whether this x exists or not. So whether this series converge or not. Okay, what's this series actually? This is an alternating sum of 1/n factorial. I think we come across this n factorial thing right just now. Have we? Yeah, we actually show that this is actually converging. Right? Okay, converge, very good. So it converge. So now we need to make sure that this bound here is less than 0.0005. Okay, is so but do you know about x? Have you computed x yet? Have you computed the infinite series yet? No, right? So you also have nowhere to check, right? But just now I told you there's an inequality between Bn and Sn, okay? So if you can make sure that Bn plus one term is less than equal, strictly less than 0.0005, then you can make sure the difference here also less than 0.005. Okay, so this is the strategy. Okay, so by remark before, if we make sure that Bn plus 1 is less than 0.005, then we can make sure that the difference is also less than 0.005. Okay? So Bn is quite straightforward to compute, right? Bn plus 1, I mean, because we let Bn to be just the 1 over n factorial. Okay. So what is Bn plus 1? Is 1 n plus 1 factorial less than 0.0005, which I think you can easily find that it is lying n plus 1 greater than or equal to 7. Okay. Which implies n is greater than or equal to 6. Okay. So what's the question asking about? Find the sum of the series correct to 7. So you need to find the sum. So you need to sum up to x6. Yeah. And then find x6. Okay. So x6 will be 3 decimal places different. Is it how I say it? No, is the 3 decimal places same as the original infinite sum? Okay. Yeah. It will differ after three decimal places. It's straightforward. Okay. So far, okay. Okay. So next. We'll talk about this absolute convergence. Okay. So we talk about absolute convergence. So if the infinite sum converge, and also if you consider the modulus of every term also converge, then we'll say that this infinite sum actually is absolutely convergent. Okay. So for example, just now we shown that which one converge? Let me see. Okay. So I guess, yeah. So for example, the sum of 1 over n factorial converges. Okay. And we just show that the alternating 1 over n factorial series also converges. Okay. Then we will say that the sum of n factorial, 1 over n factorial, absolutely converges. But let's say infinite sum of an converges, but the modulus of it, take the sum, diverges. And then we will say that the sum of an is conditionally convergent. Okay. So in particular, this is the what? This is, for example, we already come across this example. Do you have any idea? The series converge, but if you take the modulus of it, it diverge. We have come across this example just now. The alternating harmonic series. Okay, so the alternating, because the alternating harmonic series is the series that converges. So the alternating harmonic series is conditionally convergent. Okay, make sense? Okay, because the harmonic series is divergent. So we have this test here, so absolute convergence test. So if you consider the modulus of your sequence appear inside your series, okay, the term inside your series, you take modulus and then sum over them converges, then that implies that the original series converges. So maybe this is worth proving. Okay, prove this. Let's prove this. Oh, this is worth proving. So let's prove this. So we want to show that this term converges. So let us write out what we want to show. So proof. So we want to show that sum of an converges. Okay. So what to do? What to do? To do. Any idea? Squeeze. How to squeeze? How to squeeze? If you say about squeeze, you should give me some sequence that I can bound, right? With, I mean, yeah. Use area and negative. You mean something like this? Mean something like this? Is it? Is it what I mean? Okay. So what are you going to do with this? What can you say about the left and right? So what I can say about it? I only know. Okay, I think it works, right? So wait. Okay, let me see. So okay, good. So we can. So this one is an idea, right? Maybe I can check. So why we think about this? Let's say we know that this converge to 0. Okay, and this converge to 0. Okay. Can we say about? You sure? No. Wait. Let me think. So okay. Let's tell you what we're thinking about. So what we know is if the infinite sum converges, okay, then limit of an is 0. Okay, but we cannot go the other way. Right? We cannot go the other way. So because we know that this term converges, so surely these go to 0. Surely these go to 0. By squeeze theorem, this also go to 0. But from here, we don't really know whether this converges or not. In particular, we have a counterexample for this. What's the counterexample? Harmonic series. Okay. So in particular, we have this counterexample. So this shouldn't work. Okay. We still want to bound something, but we don't want to bound like this. Okay. So maybe we get bound by 0. Bound instead of bounding an, we bound an and the modulus an. Okay. So surely this thing is greater or equal to 0 because an could be minus an. So you get 0. And we can bound this by 2 times an. Okay. This is for sure we can do, right? Because if an is positive, then an plus an is 2an. Or yeah. Okay. So this is bounded by these two. Everyone following this bound? These two bound. Okay. So what do we have? Suppose the infinite sum of absolute an converges. Okay. So this means what? This gives that 2 times an also converges, right? because multiply by a scalar doesn't affect the conversion. Okay, what's next? Since this converge, right? Yeah, this guy already converged. So we have this, what do we call again? Simple comparison test. Okay, so if this series converges, this series also converges. So this also imply an plus epsilon of an converges by the simple comparison test. Okay. So in particular, these two converges, meaning can I split or not? Okay, I can split. Why? Because this is just a big sum and a small sum. You get what I mean? I'm rearranging the term. Okay, let me write out what I mean. What do I mean here? So in future, you should remember what I'm doing. So this is A1 plus A1, and then A2 plus A2, and so on. And then what I do next is I group the A1 first, and then group the AN, absolute A1, AN. Okay, makes sense. Okay, so there's nothing tricky here, just regrouping. Because this sum is literally just plus. So this is another plus. So plus, because you are commuting, it is commute. So you can do it. This one converge. Okay. Implies that implies this also converge. Is it clear why imply and converge? So suppose if you are suppose this one converge to some L, right? Okay. We know that this term also converges. Okay. So this is equal to an plus some limit equals to L. Okay. So you can move m to the other side and then find the limit for sum of an. Make sense? Make sense? Okay. Yeah, so in detail, you should write it all out. Okay, so we have shown that if we know something absolutely, not absolutely, so if you consider the absolute value of each terms appearing in the series and then you sum them all up, converges, then the original series converges. Okay. Okay. So let's try it on this example here. Okay, let you try if you can use absolute convergence theorem to show that this converges. So you should notice that this is what? What is this? Alternating P series for P equals to 2. Okay. So P series itself is convergent. How about alternating version of it? Okay. Try with the absolute convergent test. So in the absolute convergent test, what you need to do, you take the absolute value of your terms, right? Okay. And then see if this converge or not. Okay. If you take absolute, then you get rid of the alternating part, which you're left with the P series. P series is convergent. Okay. It's convergent or convergent. Convergent as is a P series for P greater than 1. Okay. So by the absolute convergent test, this alternating P series converges. Okay. In particular, this guy converges absolutely, because after you taking absolute value, you also converge. Original sequence, you also converge. Okay, so in particular converges absolutely. So both case you converge absolutely. Okay, so I think this one should be obvious because you start with a convergence series and then you add in this alternating factor in, you should converge as well. Because without this alternating series, it already converges. Make sense? Okay, at least for this case. At least for this case. Okay. So what's next? 445. Okay, let's do a long example before we break. So maybe we make this a homework and then we do a long example before we break. Okay, do this. So determine whether this series is absolutely convergent, conditionally convergent, or divergent. So what's this series, first of all? Alternating harmonic series. Yes, good. I think we have shown some version of this, right? So now we want to determine whether it is absolutely convergent, conditionally convergent, or divergent. Okay. Shown this alternating harmonic. Yeah, we have shown this, right? So alternating harmonic is actually convergent. Okay. So first of all, this is converging. We have shown it very first example we met when we talk about alternating series. So this is convergent, first of all. Okay. Now to determine absolute convergence, you need two types of series to converge, right? Either the original series converge and absolute taking absolute on every term and then sum over to infinity, you also converge. What do you get? Which is just the harmonic series. But we know that this series is divergent. Okay. So this means what? This means this alternating. Actually, this one I give as an example, right? Just now. Is it? Do you remember? Yeah, I gave this as an example actually. Yeah, and then this example asks you to show it. So by definition, the alternating harmonic series is conditionally actually there's another reason why they want you to do this question. Is there any other reason? Actually, no. I don't know why it appeared again. Should remove it next time. Okay. Anyway, you guys want to leave? Okay. Let me see. Okay, maybe let you leave. We will continue on the third day. You passing. I realized did I say something wrong? Can you bring me back your notes just now? The notes you showed me just now.